Hi, my name is Amir, and I'm going to tell you about a joint work with Pavel Rubesh about the shadows of Newton polytopes. The high-level picture that I want to paint is a bridge between computational complexity and geometry. In computational complexity, we're going to talk about problems or ideas in algebraic complexity and in optimization. And on the geometric side, we are going to talk about polytopes and the behavior of polytopes under projections. And we will see one idea, one mechanism that relates the two different universes. The starting point, the motivation for us was the question of lower bounds. The high-level question is what properties of functions make them difficult to compute. We can describe properties of functions using various structures in mathematics, using algebra, using combinatorics, using geometry. And can we use these ideas to capture something about computational difficulty? This is the high-level question. And we are going to use one such connection that was introduced by Couaran, Portier, Tavenas, and Thomas. I hope I said the names correctly. That relates algebraic computation and geometry. In the algebraic computation side, we are interested in computing some polynomial. This is an example of a multilinear polynomial, just for simplicity. These are the monomials of the multilinear polynomial, and these are the coefficients. This is the coefficient of a single monomial, C of E. And the goal we want to understand is what is the minimum number of operations that are needed to compute F. So this is the algebraic complexity side. On the geometric side, there is a standard way to associate a polytope with a polynomial. So it's done like this. We look on all the monomials, all the names of monomials. We think about a monomial as a point in Euclidean space. For example, this is a 0, 1 point, a point in the discrete cube. And we look on all such points where the coefficient of the corresponding monomial is non-zero. This is some finite subset of Euclidean space. And then we just take the convex hull of this set. This is a polytope. And this is called the Newton polytope of the polynomial F. So we get it from a polynomial, we get some polytope, which is a geometric structure in Euclidean space. And the high-level connection that they wanted to understand, or that they suggested, is that the computational complexity of this polynomial is related to some properties of this polytope. This is helpful because on this side, we may be able to use geometry to prove things, and hopefully these things will then translate back into the computational complexity world. So this is the high-level suggestion. When we translate to the geometric side, we need to somehow discuss the complexity of a polytope. So here is, we made their suggestion explicit. So here is the underlying complexity measure that they suggested to study. We call it the shadow complexity of the polytope. It is defined like this. We have the polytope P. We can take a linear map from Rn, where P lives, to the plane, and project the polytope onto the plane. This is L of P. Now we have a polytope in the plane, and we can measure the number of vertices of this polytope. And then we can choose the linear map L, the projection L, that maximizes the number of vertices. And this maximum is called the shadow complexity of the polytope. So this associates a natural number with every polytope, and it captures some aspect of the complexity of the polytope. Specifically, it was before we introduced it, it was studied in geometry. And a specific example of such a study is this theorem of Moser, who studied polytopes in three-dimensional space with n vertices, and asked what is the minimum shadow complexity of such a polytope. And he showed that the minimum shadow complexity is of this order of magnitude, log n over log n. And I want to mention that this is a minimax problem. So this is the minimum over polytopes and the maximum over linear maps, and then some number that depends on the polytope and the linear map. So Moser solved this minimax problem in three-dimensional space. And going back to computational complexity, this is the, in a high level, the suggestion that was made by these people that relate the computational complexity of F and the shadow complexity of F, which is defined to be the shadow complexity of the Newton polytope. So there is a suggestion to investigate the relationship between these two complexity measures. Specifically, they suggested that if the shadow complexity of the polynomial is high, then it follows that F is difficult to compute. And this is a mechanism for proving lower bounds, potentially. This is a conjecture. It's not a theorem. They conjectured a statement of this sort. I will not formally state the conjecture, but I will talk about related ideas. So this shadow complexity, following this suggestion, is a mechanism for proving lower bounds. This is the high-level idea. And the first thing we verify or prove or observe is that this high-level suggestion is actually true. This conjecture is true for monotone computations. So what is a monotone computation? Here we compute polynomials over the real numbers, and we can compute without cancellations. We can use only positive numbers in the computation. So we first show that shadow complexity is a lower bound on the monotone formula complexity. This is true for every polynomial. So shadow complexity in the monotone formula model is a lower bound, always. And we also show that for some specific family of polynomials, shadow complexity is a lower bound on the monotone circuit complexity. And what is this family of polynomials? The family of transparent polynomials. A polynomial is transparent if its shadow complexity is equal to the number of its vertices. So when we project the polytope to the plane, all the vertices of P are vertices of the projection. For such a polynomial, shadow complexity implies monotone circuit lower bounds. This theorem is relatively simple to prove using known properties of polytopes in the plane. This theorem is more complicated, and it uses monotonicity in a very strong sense that was used in previous works as well, that you cannot undo a structure in a monotone computation. So I will not explain the proof, but this is relatively simple, and this is more elaborate. You need to pay more attention to what is going on. And the summary of this is that this tau conjecture is true for monotone computations, which is a good sign for the program. But perhaps a less optimistic sign for the program was made by Michael Forbes. So he observed that the Newton polytope of the permanent is exactly the same as the Newton polytope of the determinant, because they have the same monomials, just different coefficients. And this polytope is the polytope of doubly stochastic matrices of fixed size, which is also called the Birkhoff polytope. And we believe that the permanent is hard to compute. We know that the determinant is easy to compute. So how can it be that the Newton polytopes are the same, but still it contains useful information about computational complexity? This is equality, and we believe that these two polynomials are very different. Specifically, this observation shows that if the shadow complexity of the Birkhoff polytope is exponential in n, then this tau conjecture, this program for proving lower bounds, is false. This is a question that we tried to understand, understanding the shadow complexity of the Birkhoff polytope. So we want to understand the shadow complexity of the Birkhoff polytope. This is a purely geometric question, but before we can answer maybe this complicated question, let's first just try to understand shadows of polytopes. What can we say about them? So I want to start with an example. We have the hypercube. Here it's the solid hypercube in n-dimensional space. It has 2 to the n vertices, roughly n times 2 to the n edges, and we want to project it to the plane. And we want this projection to have as many vertices as possible. So we have 2 to the n vertices. We want to project to the plane with many, many vertices. And just as an example, I want to show that this question, this projection is not very powerful. So for example, the shadow complexity of the solid cube in n dimensions is exactly 2n. And one can prove this using 3 methods that are, I want to go over them quickly. One is to use the connection to algebraic complexity. So this is a monotone formula. The size of this formula, the number of leaves in this formula is 2n, so 1 plus x1 is 2, and then n products. And the Newton polytope of this polynomial is the solid cube, because all monomials appear in this polynomial. So this is a monotone formula of size 2n. We saw that the shadow complexity is a lower bound on the monotone formula size. So we see an upper bound of 2n here. So this is one connection. The second way to prove it is using zonotopes, which is a family of polytopes. So a zonotope is a polytope that is obtained from line segments, these are the building blocks, and Minkowski addition, Minkowski sum. This specific family of polytopes, zonotopes, is particularly easy to understand in many cases. And also in this case, the fact that the hypercube, the solid cube, is the Minkowski sum of n perpendicular line segments. The perpendicular is not important, just the fact that it's a sum of n line segments gives us an upper bound again of 2n. So this is a geometric perspective. The third is less accurate, but it allows us to understand in a high level why is it true that the shadow complexity of this polytope is small. So this is what I want to discuss next. It's connected to optimization. So here I move shortly to optimization, briefly to optimization. Here we want to optimize a linear function to find the maximum of a linear function over a polytope P. This is the direction, and this is the polytope, and this number is the maximum of this linear function over the convex polytope P. This is a very standard optimization problem. And in parameterized complexity, there is some mechanism, some idea to measure the complexity of this optimization problem. So P is the thing we want to measure the complexity of. How do we do this? We look on a one-dimensional space of weights. So we look on A, a vector A, fixed. We look on a vector B, fixed as well. And we allow to multiply B by some real parameter T, which I will call time. So at time T, there is some weight W of T. This is a vector in Rn. Now for every T, there is the maximum over the polytope of this linear function depending on the weight at time T. And I denote this function by phi of A, B, A and B at time T. So we have a one-dimensional space of weights. From it, we get a function from the reals to the reals. because this is a maximization over a convex polytope, this function phi of AB is piecewise linear and convex. Such a function has breaking points. These are the positions, the times at which two vertices are maximizers of this linear function. So we started with a polytope. To measure its complexity, we defined a one-parameter family of one-dimensional family of weights. From it, we got a function from the real to the reals. And now we have a number associated with this function. Its complexity is its cost, perhaps, is the number of breaking points. So this leads to the following definition. The complexity of the polytope P from this perspective is the maximum over all vectors A and B that determine one-dimensional weight, parameter one-dimensional family of weights. For every A and B, we measure the number of breaking points and we take the maximum. This is the complexity measure associated with P, the number of breakpoints in P. And this is another complexity measure that is associated with a polytope P. It was used by Mulmuli, for example, to prove lower bounds in some concrete computational model, the model of PRAM without bit operations. Now I want to go back to shadow complexity. So we first observe that the number of breakpoints of this polynomial is equal up to a factor of 2 to the shadow complexity. So these two quantities are basically the same. This is one thing we prove, one thing we observe. And another is that the perspective of optimization allows to prove upper bounds on the shadow complexity. So here is a rough statement. If the optimization problem over P, the one that we just described, can be solved via a greedy algorithm, then the shadow complexity of this polynomial, of this polytope, is small. So an easy polytope in the sense of greedy algorithm yields small shadow complexity. And because specifically the optimization problem over the hypercube can be solved greedily, this implies that the shadow complexity of the hypercube is small. Now, we can also use this connection to address to get some starting point in the tau conjecture that is related to the tau conjecture. So Cartensen and then later Mulmuli and Shah simplified the proof of this fact. The number of breakpoints of the Birkhoff polytope. The Birkhoff polytope corresponds to finding the maximum matching in a weighted graph. This is the maximization problem. The number of breakpoints of this maximization problem is super polynomial. This was proved by Cartensen. Because of our observation that I just explained, we get a lower bound on the shadow complexity of the determinant. The shadow complexity of the determinant is equal up to a factor of 2 to the number of breakpoints of the Birkhoff polytope, which is at least this number. This was proved by Cartensen. On the other side, we can also prove this is a different argument, that the shadow complexity is at most exponential in n. This is not very impressive, but it is not trivial in the sense that the determinant has n factorial monomials. So when we project it to the plane, the vast majority of the vertices disappear. The number of vertices become tiny compared to the original number. And so this is the best bounds we know on the shadow complexity of the determinant. Now, the interesting question is to understand what is the truth. This is the truth, or this is the truth. I want to mention that although this upper bound is super polynomial, which we think of typically as being large, this lower bound does not violate the tau conjecture. To violate the tau conjecture, we need a lower bound that is closer to exponential in n, because this is the specific way the conjecture is built. Okay. So this lower bound does not violate the tau conjecture, but it shows that the determinant is not super easy in some sense. Another comment I want to mention is that the shadow complexity of the determinant, as I said before, is related to finding the maximum matching in a weighted bipartite graph. Finding such a maximum matching can be solved in polynomial time. So perhaps there is a way to use this algorithm to show that this is the true upper bound. We were not able to do this, but it is certainly possible that this is the truth. I want to summarize the whole picture I painted. So we introduced a complexity measure that was that appeared in a few contexts. So it appeared in geometry because of geometric motivation. It appeared implicitly in algebraic complexity because of its conjectured connection to lower bounds. And it appeared in optimization in the form of parametrized optimization and the connection to the PRAM model. So we do not yet understand this complexity measure, but it is a clean framework to study complexity type questions in a geometric framework, and it may lead to new understanding of two computational complexity worlds. And in the paper, there are more details, more results that I'm not going to mention right now. You are welcome to look. And I thank you very much for the attention, and I hope to actually meet all of you soon. So thank you.